click on recording. Okay, so I'm going to back up one step. We have situations where we take a single sample and we want to compare it to a known population that we might have some information about. We know the population of the mean of a certain population. We don't know of another population, and we take sample that population. We want to compare it and see if we can predict that the two population means are equal to each other. Remember, the end game here is really we want to, with some confidence, be able to say two populations have the same mean or two populations have different means. Our mechanism for getting to that point is to analyze samples. We never really have an opportunity to know what the population means really are, but that's really what we're concerned about. The sample means are very nice to know, but we're using them as an estimate for the population means. That's the real end game here. So very rare situations, we might know a population mean for one population, but not for another. For instance, I might know the average mean total cholesterol level for all Spaniards, but I don't know what it is for Americans. So I might want to compare whether or not there's a difference in those two populations. Since I don't know it for Americans, and I don't have the resources to sample everyone's blood in the United States, I might take a random sample of, say, 100 people in the United States. Now I have a sample mean, and I want to compare that to a known population, the Spanish total cholesterol. Okay, in that situation, I have a sample mean and I have a population mean. I want to compare the two of them. That's a single sample hypothesis, that t-test or hypothesis that we're going to test. Now, in some cases, we don't know either population mean, so we have to take a sample of of 100 Spaniards, compare them to a sample of 100 Americans. And in that case, we're taking two samples and comparing the two of them to try and determine whether there's a difference between those two population means. Okay, in that case, we're doing a hypothesis test that involves two samples. Now, since we don't know not only do we not know the exact means of those two populations, but we don't know what the variability of the cholesterol is in those two populations. So I don't know the standard deviation for either population either. Fortunately, the sample gives us a window on that. It gives us an estimate of what the population standard deviation is for Americans and for Spaniards. But there's a little bit of a catch there. In some cases, we might do an analysis with these two samples. We might find that the variability among Americans is much greater than the variability among Spaniards. So now not only do I have a situation where I might want to be comparing two samples, but some of those two samples might have equal standard deviations between the two populations or appear to have equal standard deviations. Some of them may have different, unequal variations between the two of them. So now I have to have one mechanism for dealing with it when we have equal standard deviations or variances, and another mechanism for when we have unequal standard deviations. Those are the first two descriptions that we see here in this kind of reference. Okay, next, we've been dealing with proportions as well. So for instance, we might want to know what the proportion of Spaniards are diabetic and what proportion of Americans are diabetic. So now we're comparing, and again, we're going to be working with samples. So now we're comparing a sample, a binomial sample for Americans and for Spaniards. How many out of 100 are diabetic? How many out of 100 Spaniards are diabetic? I want to compare the two of them. So we have to be able to compare two proportions for two samples as well. So we have another whole set of formulas for that. Okay, so there's a lot of situations that we're going to run into here. And what we're going to do is we're going to work our way through these with some simple examples. We're going to take a step back for starters, and we're going to take a look at a single sample hypothesis test. Okay, and what is our sequence here? The first thing that we want to do when we examine a hypothesis is, what do? What's number one here? State your null and alternative hypothesis. Okay, so let's do a single sample hypothesis test where we know the standard deviation of the population, where we know of the two populations. So let's say they're equal, and we know the standard deviation. We know what sigma is. Okay, so I'm going to do a single sample t-test with a known standard deviation. So here's a sample I put together. It's just, it's 9 numbers, right? Is it 9 numbers? 1, 2, 3, it's actually more than 9. No, it is 9 numbers. Okay, and sigma happens to be equal to 3. And I want to test the mean for the population that this random sample is taken from against a population with a known mean of 8. And I want to have 95% confidence that I'm right and reject a null hypothesis. And in other words, I'm willing to accept a level of type 1 error, an alpha error, equal to 5%. Okay, everybody comfortable with that so far? Okay, so how would I actually go about doing this? Well, let's see. This is a pretty simple one. I'm going to open up Excel. And in fact, I think if you look on Blackboard, I actually made an Excel file for us to work with. Okay, here we go. And here's the same numbers. And 6, 7, 8, so on and so forth. Oops, I changed one of the numbers there. Okay, we'll work with the numbers I have in Excel. Here's our sample, and we're going to want to compare this to a mean of 8. So what's our null hypothesis? What's that? What is that? Mu 1, right? Mu 1, our first population mean is equal to 8. The population mean for the population that we drew the sample from, the mean for that population is equal to the value of the other population's mean, which is equal to 8. What's our alternative hypothesis? That they're not equal to 8, right? Mu is not equal to 8. Okay, good. And what level of confidence do we want to have? What's alpha? 0.05. Okay, now we know sigma, correct? Okay, so that means that I use, what kind of distribution can I use? The Z distribution or the T distribution? I can use a Z distribution, right? And for an alpha of 0.05, let's say it's two-sided. We don't know whether our population is greater or less than 8. So it's two-sided test. So for Z for alpha over 2, or for a two-sided test, the Z-score, which is going to be our critical value, the Z-score has to exceed this number for us to have a p-value less than 0.05. What does our Z-score have to be? It's going to have to be 1.96, right? Because we know that for Z-table, have 2.5% on one end and 2.5% on the other. It's got to be smaller than negative 1.96 or bigger than positive 1.96. It's got to be outside of that range in order for us to have a p-value. So I can even use that kind of idea of a critical value with the Z-table as well as with the T-table, because I'm just looking at how big it has to be for me to know whether or not I can reject my null hypothesis. With the Z-table, it's going to be easy for us if we really want to calculate our p-value, right, if we want to. Right, but really, since we're just at this stage just trying to decide whether we can reject the null hypothesis, maybe I don't have to do this. Maybe I can stick with this for now. Okay, so let's go to Excel. The mean for this sample is going to be average, and the average of all these numbers. Well, the average is 10. Standard deviation is 2.73, et cetera, and the standard error is equal to, what's standard error going to be equal to for single sample t-test? It's going to be equal to the standard deviation divided by the square root of the sample size, which is 9, right? Square root is 3, so I'm just going to divide, I'm not going to bother to put square root, I'm just going to divide it by 3. So that's equal to 0.9128. So now, how do I calculate my Z-score for the difference between these two means? How many standard deviations apart are these two means? Well, I seem to remember that what we do is we say to ourselves, it's equal to X bar, which is 10, minus the mean, which is 8, right, over our standard error, right, to get our number of standard deviations. Let's see if that works. What's our Z-score? 2.19. Is that enough to reject our null hypothesis? We exceeded 1.96, so it's far enough apart that we can say, with less than 5% chance of being wrong, that we can reject our null hypothesis. And what's the other part of that? Reject our null hypothesis and accept or reject our null hypothesis, right? And accept the alternative hypothesis. Now, what if we didn't make it? What would we say about the null hypothesis if we didn't make it? I think at the end of the lecture there, we decided that just because we don't reject the null hypothesis doesn't mean that we've proved that the null hypothesis is right. Instead of saying that the null hypothesis is true, what do we say about the null hypothesis if we fail? We just say we fail to reject the null hypothesis, right? We don't accept the null hypothesis. We just say we fail to reject it, because that's really how this is all structured to work. To force us to prove to a certain level of acceptable level of error that we can reject the null hypothesis with that level of confidence. Okay, so now what happened? What changes here? I'm going to go back here, single sample t-test with sigma known. What changes here if I don't know what sigma is? Well, now, where am I going to get my standard deviation? Oh, my goodness, what did I just do? I just did a t-test, didn't I? Right? I should have used, if I had remembered what the hell I was doing, I would have used 3 for the standard deviation, right? And then my standard error would have been 1, and my Z-score would have been 2. I still would have rejected, just barely rejected, because it's bigger than 1.96. But now I'm going to go back, and now I do it myself using the standard deviation of this actual sample, and and in fact, my t-score is equal to 2.19. Well, what level? How is that big enough for me to reject the null hypothesis? What do we need to look up now to decide whether we can reject the null hypothesis for this t-test? Well, the critical value of t, we need to get that from our table, right? So let's open up our t-table. And I'm pretty sure I have it on Blackboard. Let's see, Agresti, I think. Here we go. Here's the t-table. Okay. Yes, I'm recording, guys. They were querying me at home. Okay, so we're at t is equal to 0.025, right tail prob, one single tail probability is 0.025, alpha over 2 for a 95% confidence interval. Alpha is equal to 0.05. Okay, so now what's our sample size? It's 9. So our degrees of freedom is 8. So what's our critical value for t? 2.306. Okay, so now if I go back here, have I exceeded my critical value? So now what happens now? I fail to reject the null hypothesis. Okay? Yes?
Why are you testing t-score if the sigma is known?
I'm sorry, say again?
Your scenario is that to use the t-score t-test. If the sigma is already known.
Oh, no, I just repeated it, except, see here, in this version, 2.73, that was calculated from these numbers from the sample itself. See the standard deviation? Mm-hmm. The first time around, I used 3 to get a z-score of 2, right? Because standard deviation is 3. The standard error would have been 3 over 3 is 1, right? And my 10 minus 8 over, which 2 over 1 would be 2. So my z-score would have been 2, right? Which is enough to reject the null hypothesis because it's bigger than 1.96. But now this is my t-score because I'm not using 3, I'm using 2.73 for the standard deviation. And I got that. How did I get that again? That's equal to the standard deviation of my sample, not the presumption that I knew the population standard deviation. That's where that 2.73 came from. Okay? Are we comfortable with that? I'm sorry, I kind of had to go back around the corner on that. Yeah, I kind of lost track of what I was doing with the standard deviation. Do we all understand that reasonably well? Yes? Okay, good. All right, so let's see what we can take a look at next. Okay, so now that's how we would handle a single sample comparing it to a known population. So now let's take another, before we move on to that, let me just do one more thing here. I'm going to open up that same data set in SPSS. Let's say you worked out this problem. We gave you this problem on the exam. And you worked it all out. You got an answer. You got a T-score. You decided whether or not you could reject your null hypothesis and so on and so forth. But you wanted to check your answer. Well, why not open the data in SPSS as well and do the same test in SPSS? And in fact, maybe on the test, we'll actually ask you to do one of these examples in SPSS, give you the data file, and ask you to work it out in SPSS. Okay. Okay, good. Okay, here's the same data set opened up in SPSS. I'm going to go into Analyze. And remember, I'm doing a t-test here, so what am I doing really? I'm comparing means. Compare means, in this case, is a one-sample t-test. Okay, one-sample t-test. Here's my variable, happens to be called x. I'm going to move it into my test variables. The options are probably already filled in. It's going to say confidence interval 95%. If your alpha is 1%, you might change that to 99. Okay, but it's probably the way we're going to use this. Now, I'm going to tell it now what the mean is that I'm testing it against. Remember what I said the known mean was for the other population? It was 8, right? Okay, so I'm going to click OK. And let's see what I got. I got 10 for the mean of my sample. I got sample size of 9. I got standard deviation of 2.739. I got a standard deviation of 0.913. These numbers should look pretty familiar because that's exactly what we calculated. And what was the t-score that I calculated? T is 2.191 for 8 degrees of freedom. And my significance, my p-value, my probability of being wrong if I reject the null hypothesis, or the probability that I could get this extreme of value and the two populations really be the same, okay, my probability is 0.60. What do I need to reject the null hypothesis? What does that significance or p-value have to be? Has to be smaller than 0.05. So it isn't, so I, again, failed to reject the null hypothesis. Same answer as we got before. So we can use SPSS to do this rather than do it manually. Okay, next. Okay, good. I'm going to get this out of the way. Okay, so now look at the next variation of this stuff. Two-sample hypothesis testing. Okay, this time around, to start off with, I'm going to make the assumption, and we're really going to assume it now. We're going to not worry about calculating it, examining it, or anything like that for now. We're going to take this set of numbers, and we're going to deal with it two ways. The first way is I'm going to make the assumption that the variances are equal. So let me see. Well, let me go back here and see what I have to do first. State your null and alternative hypothesis. Okay, what's H null? Okay, what's equal? The two means of the two populations are equal, right? Not X bar is equal to X bar. Mean 1 is equal to mean 2, right? Our alternative hypothesis, right? That they're not equal. Mean 1 does not equal mean 2. Remember, this is all about the means. Okay? And now, what level of certainty do I want to take this to? I don't say it on here, but let's say my alpha is going to be 0.05. I thought I did somewhere, but let's say that we didn't. Okay, so now I know my two means. I can calculate my two means, right? But now I mentioned that it's equal variances. These two groups, even though the means look like they're going to be different, I'm saying that the variances, the variability within these two groups is about the same, for argument's sake. Okay, so now if the variances in the two groups are the same, well then why don't I just combine the two groups to see what the variability is. Because in other words, if it's the same variability, by combining the two variabilities, I can have a little bit more confidence that I have a good estimate of what the true variance is, the true population variances are. Make sense? Instead of trying to figure out what the variance is based on a sample of size 9, and then do it separately for this other group sample of size 9, since I'm assuming that they're equal, why not combine the two of them, the two variances, and say that I can determining the population variances based on a sample of size 18? Doesn't sound like it would give you a better estimate of the sample variance? Yes? You guys agree with me, or does that trouble you guys? You know what I'm saying? In other words, I increase the size of the sample I have to usefully use to calculate the population variance. But that assumes that both of them are the same, because if they're different, that doesn't make any sense to combine the two of them, does it? Right? Okay, but if they're the same, and there's a lot of situations where we would have a good argument for saying that there's no reason for them to be different. The means may be different, but why would the variances be different? There are a lot of places that is likely to occur. Okay, we may know that because of the nature of the data, nature of the measurement we're making. We also may be able to predict that based on a calculation that we can do to test these variances to see if they're the same. And SPSS actually does that. Every time you do a t-test, a two-sample t-test with SPSS, it actually calculates how likely it is that these two variances, these two populations are equal. Okay, so we're going to make the assumption that they're equal, and we're going to try and combine the two standard deviations. We're going to call that combined standard deviation the pooled standard deviation. So if I go back and look at this reference here, what do I have here? Calculate the pooled standard deviation. How do I calculate that? Well, it's a sample size. I take a look at the two samples. It's sample size 1 minus 1. That's, in other words, that would be, I'm going to pull up Excel. And I'm going to get myself a fresh area to work with here. The sample size, let's see, my pooled standard deviation, n minus 1 is 8, right? Sample size is 8. What's the standard deviation of this group? Well, you want to know something? I actually have an Excel file that has this data in it. It's on Blackboard also. I'm going to open it up. Which one of these two is the Excel file? Two sample t-test. Oh, okay, let me blow this up a bit. Okay, good. Let me get bigger. Okay, here we go. In fact, I call this males and females for the two groups. Okay, so now let's calculate all of these different things. X bar 1. Okay, X bar for males. What's that equal to? It's equal to average and parentheses, and the average is 10. Okay, X bar for females. Okay, that's equal to average, parentheses. Okay, females is 7.5. Okay, let's calculate standard deviation. Standard deviation for males, standard deviation 1 is equal to standard deviation. Since I don't know the population standard deviation, I have to get it from the sample. And standard deviation 2 is equal to the standard deviation for the female subjects. And that comes out to be 1.94. Doesn't really look like they're the same, right? However, we're gonna keep going on the assumption that they're the same. They're not really that different. So I don't think that's too much of a stretch. But for this first example, we're going to assume that the standard deviations for the two obviously for the samples, they're always going to be different. You're never going to get virtually never going to get a sample where the two standard deviations are the same, because you're just calculating them from different numbers. Okay, that would be very rare, even if the population standard deviations are really the same. So I'm going to say that's close enough to call them the same. Okay, so now I'm going to go ahead and actually calculate my standard deviation pooled. Okay, so let's see what that's going to be. That's going to be equal to And let me put a parentheses here to start off with. What's that going to be equal to again? It's going to be equal to, it's going to be equal to n minus 1, which is 8, times the standard deviation squared. Well, okay, what was our standard deviation? It was 2.73. Tell you what I'm going to do is I'm going to hit escape there. I'm going to square it up here, make it a little easier. What's the square of the standard deviation, by the way? It's the variance, right? Yeah. So we're just actually calculating the variance, kind of backing up and going back to the variance. Okay, standard deviation pooled is going to be equal to 8 times, 8 times, and let me get up there and click on it, 8 times 7.5 plus 8, that other sample size is 8 also, as it happens, times the standard deviation for the females, which is 3.78, 3.77, close parentheses, and all of that's going to be over n1 plus n2 minus 2. What's that? That's 8 and 8 is 16. That's going to be over 14. Okay, and I got to take the square root of this whole thing. Okay, well, first I'm going to put parentheses around this so that it actually adds them before it divides by 14. And then I'm going to take the square root of everything. Put another set of parentheses around there. Okay, cross your fingers. How many people think this is going to work right off the bat? N2, what's on the bottom? N1, how much is N1? Oh, yeah. Oh, 16. Excuse me. I subtracted 2 twice. Okay, and okay, let's give it a shot. Oh, it worked. What do you know? Okay, so my pooled standard deviation is 2.37. It's in between the two standard deviations, isn't it? Okay, so let's move on and actually apply this. Okay, so now what are we going to do? We're going to calculate a t-score. And how we, oops, did I do something wrong here? What did I do here? Oh, you want to know something? Did I put this in the wrong spot? Unequal standard deviations. What did I do wrong here? Oh, Levi, did I lose a formula here somewhere? Did I lose a formula here somewhere? I want to apply the pooled standard deviation. Where'd it go? I have equal variances. I calculated my pooled standard deviation, but the formula here is for unequal standard deviations. Where did my formula go? How did that happen? Let me go back. See, this is for unequal standard deviations. Oh no, wait a second. That should be pooled. Is that S1 pool? Those are the two. No.
Got S1 twice there.
Yeah, there's something wrong with that formula.
That should just be SP.
SP.
It's SP instead of S1.
Sure about that? Doesn't have to be outside. Oh, you know what it is? I'm used to seeing SP outside of this.
Right, yeah.
And then 1 over N1 and 1 over. That's it. Okay. Yeah, I don't like this formula. I like it the other way. Okay, it'll work out either way. Hey guys, another way of showing this formula, this is the pooled standard deviation squared inside this box. Another way of showing this, since they're both squared and they're both added together, is to factor that out into the standard deviation pooled squared times 1 over N1 plus 1 over N2, right? So in that case, the square root of it would be the pooled standard deviation, which is outside. You could take it outside the square root. So I'm going to calculate it. I'm going to calculate it just the way it's shown there, so I don't confuse you any more than I already have. Okay, so let's calculate what t is equal to. T is going to be equal to x bar 1 minus x bar 2. And what were they again? 10 minus 7. Okay, 2.4. That's x bar 1 minus x bar 2. That's my numerator. Now I'm going to calculate my denominator. That's equal to the square root of my pooled standard deviation. I got to change that to a variance again. Let's change that to a variance equals pooled standard deviation times pooled standard deviation. Okay, so I'm going to do that again. Equals the square root of the pooled standard deviation over the sample size 1, which is 9, plus the pooled standard deviation, variance rather, over the sample size 2, which is 9 also. Close parentheses and hit enter. So t is going to be equal, here's my numerator, here's my denominator. So t is going to be equal to 2.44 over 1.119, which is equal to 2.18. That's my t-score. Can I reject my null hypothesis? Yes or no? What do you think? Did we know the population standard deviations? No. It's a small sample. It's only 9 each, right? So what do I need to, what's my t critical going to be? I have to go to my t table to determine what t critical is going to be. And what did I say? What did I say my degrees of freedom were going to have to be? It's going to be n1 plus n2 minus 2. So that's how many degrees of freedom? 9 and 9, 18 minus 2 is 16. Let's go back to our Agresti t table. I got rid of, there were 2 formulas there. I got rid of the wrong one. Okay, so 16 degrees of freedom. What does our t-score have to exceed? 2.12. Okay, our critical value is 2.12, and what did we actually calculate? 2.18. Can we reject our null hypothesis? Yes, we can. Okay, just barely. Right? Okay, so now let's repeat this, assuming unequal standard deviations for the 2 populations. Okay, since they're unequal standard deviations for the populations, take a look at the formula here. Number 3, the formula that we have for unequal standard deviations. Did you notice that instead of having the same standard deviation, the pooled standard deviation here, we have standard deviation for group 1 and standard deviation for group 2. We keep them separate. We don't calculate a pooled standard deviation. Okay, so let's do this. So now, okay, let's calculate this now again, except this time I'm going to calculate it for not a pooled standard deviation. So I'm going to get rid of all this stuff about the pooled standard deviation here. So again, my null hypothesis, mu1 is equal to mu2. Alternative hypothesis, mu1 is not equal to mu2. Mu for females, males not equal to mu for males. I calculate my mean for my sample of males, calculate my mean for my sample of females, calculate my standard deviation for males, calculate my standard deviation for females from my sample, correct? Okay, and now I have to calculate my t-score. And what is my t-score going to be equal to this time? Well, the numerator is going to be the difference between the 2 means, right? Which is going to be 10, equals 10 minus 7.5 or 2.44. My denominator is going to be equal to, the square root of my variance, which is my standard deviation squared for group 1, which was 7.5, good. Okay, divided by my sample size for the first group, which was 9, right? Plus my variance for group 2, right? Which is, did I click in the right spot? F7, yes. Okay, over my sample size for group 2, 9 again, close parentheses, and I'm going to hit enter. Okay, now let's calculate my t-score now. T is equal to, it's going to be equal to, let's see what's going to be equal. It's equal to x bar 1 minus x bar 2 over my standard error, which is calculated here for 1.19 divided by 0.19, and my t-score is 2.1836. Is that much different than the one I got before? And very frequently you won't see that big a difference. I'm going to do something interesting now. I'm going to open up this same problem in SPSS. SPSS, every time it does a calculation for two independent groups like this, males and females, diabetics, non-diabetics, blood sugars or something like that, every time it does an analysis for two groups, whether it's equal variances or unequal variances, it actually calculates the score, the t-score both ways. And we're going to take a look at that right now. Okay, here's, let's see. Again, this is on Blackboard. Later on or now, if you want to do it as I'm doing it, you can just open up these files. This one's on Blackboard, 2 sample t-test. Okay, and here's my data. Now, interestingly enough, SPSS doesn't like the idea of listing, it's not Excel, doesn't like the idea of listing males in the first column, females in the second column. Males and females, that's a variable, right? That's a nominal variable. Either each person, the second person, the fifth person, they're either male or female. So in one column, we put their gender. In the other column, we put their the result for whatever this test is, right? Whatever X is, whether it's, I don't know, number of seizures per year or something like that, right? We put that into this other column. So now SPSS can analyze this using two variables. Doesn't like doing it the way Excel does, except when they're paired samples, when they're the same variable for two different groups, where the patient going across same patient before and after, for instance. Okay, so now we have two variables here. Now, what do I do to analyze this? Do my t-test, compare means, same thing. Do my t-test, compare means, same thing. Where do I go? Analyze. Somebody want to give me a hint? Compare means. Now, what kind of sample is this? Oh, not paired. Independent. They'd be paired if it was a patient's value before and a patient's value after, okay? Independent, they're males and females. Okay, so now into the test variable, I put the variable that I'm going to calculate the mean for, which is x1. Into the grouping variable, I'm going to put the variable which is going to break up my two groups. It's going to factor my two groups and factor these results into two groups, two different means. I got to define the groups. Now, as it happens, you can't see it right there. Whoops. Did I do something wrong? What happened?
It's opening.
Yeah, it bangs there. Okay, cancel. Let me do it again so it pops. Doesn't like coming up here. Okay, I got to tell it what those values are for those two groups. Let me see if I can't get into this. I'm going to, just so you can see, before you, remember that if I go into the variable view here, you can see that for gender, number 1 represents male and number 2 represents female. SPSS, I need to tell SPSS that that's the case, that the variable is actually 1 and 2, not male and female. So define groups, I have to tell it that group 1 has a value 1 and group 2 has a value 2. It will then interpret it from there as male and female. Okay, if I go into options, it's going to show me the level of confidence that it's going to do the calculation for, 95%. So I'm going to leave that the way it is. And I'm just going to click OK. Okay, let's see what we got. Two sample sizes, 9 and 9. Mean, 10 and 7.56. A little bit different than we had before. I don't remember. Okay, standard deviation, 2.739. Standard deviation, 1.944. Same thing we got before. Standard error, 0.913. Standard error. Well, we didn't calculate two separate standard errors, did we? Right, at any point. We actually went through our calculation for the t-test. Okay, so let's take a look at our t-test. The first line across is our t-test assuming equal variances. The second line across is our t-test assuming, not assuming equal variances. Okay, so it actually did this both ways. Let's see what the t-scores were. In both cases, they were 2.184, 2.184, the same value that we got. Now, the degrees of freedom. When we said equal variances assumed, it used degrees of freedom equals 16. I didn't show you something about degrees of freedom for unequal variances, for equal variances not assumed. We're going to get to that in a second. There's a reason why I didn't show it to you, okay? Because it's pretty ugly, right? You saw the formula ahead of me, so it's pretty ugly. So I didn't bother to show you that yet. I'm going to go back to that. Okay, so let's take a look at what our results were here. Okay, the degrees of freedom are slightly different, so the significance comes out a little bit different. The probability of being wrong comes out a little bit different. Okay, in both cases, they're less than 0.05. So in both cases, we would reject our null hypothesis. Okay, anytime the p-value is less than 0.05, the two-tailed significance, again, SPSS uses significance to represent the p-value, the probability, is less than 0.05, reject the null hypothesis. So now, let's take a closer look at this. How would we have decided whether or not to use equal variances or to not assume equal variances? Well, I look at these two numbers, 2.7 and 1.9. One of them is like, I don't know, 3/4 of the other. It's a pretty big difference, it seems like. But then the magnitude of these two numbers is not that. It's not like one is 1 and the other is 10, right? Magnitude is not very, it's kind of hard to make a judgment on this. SPSS actually does a test, and it does something called Levine's test for equality of variances. Okay, what do you think the null hypothesis is going to be if it's going to do a test for equality of variances? Is it going to assume for a null hypothesis that the variances are equal or different? What's your history of null hypothesis? Yeah, anytime we do a null hypothesis, we're kind of assuming that the variances are equal to start off with. And this is exactly what's happening in this box right in here, Levine's test for equality of variances. So SPSS does this mathematical test, and it happens to give the value of the statistic. It calls it F. F is used in a lot of, that letter is used for some other applications in statistics, not necessarily related to this. But it says that statistic comes out to be 1.45. That represents a significance, a probability of being wrong if we reject the null hypothesis of 0.245. Should we reject the null hypothesis that the variances are equal? No, because it was not less, the significance not less than 0.05. So we're not going to reject the assumption that or the null hypothesis that they're equal. So if we were going to use, which of these two lines should we use then? Well, we're going to stick with the top line because we didn't have enough information to say that let's reject the hypothesis that the variances are equal and accept the alternative that they're not equal. So we're going to stick with the top one since that p-value was not less than 0.05. So we would just ignore the bottom line and use the t-value and the significance for the top line. Okay. In which case, do we reject our null hypothesis? Yes, we do, as we did before. Actually, we would have in both cases. Questions on that? That's got to be confusing, right? Yeah, I can tell by your face it's confusing. Ask me a question. Is it so confusing you can't come up with a question? Is that it? Because I'll do it again. I'll do another set if we want to do that. Yes?
So, the test, would we have to run that before assuming which one to choose?
Well, to be honest with you, SPSS, not really, because SPSS does both. In other words, you could conceivably run it before. So you could decide, if you were doing the calculation manually, you could decide which test to run, assuming equal variances, not assuming equal variances. But if you're using SPSS, why bother? Because it's going to do both calculations anyway. So you can decide after you run the test which of the two to use. Okay, I'm sorry.
What's the significance column in the Levine
The significance where?
in the Levine test?
That is the significance. Remember, Levine's test is a test just like any other statistical test where we have a null hypothesis. Our null hypothesis is that the variance 1 is equal to variance 2. Equal variance is assumed, right? Our alternative hypothesis is equal variances are not assumed, that they're not equal. Variance 1 does not equal variance 2. That's the bottom line. The Levine's test tells us whether or not we can reject that null hypothesis that equal variances are assumed. So the significance, the probability of being wrong, if we forget about the top line and use the bottom one instead, in other words, you reject the idea that they're equal and instead accept the idea that they're different and use the bottom line instead of the top line, our probability of being wrong is 24%. But that's too big a probability. We don't want to accept that, right? Usually we don't want to accept a chance of greater than 5% of being wrong, an alpha of 5%. So we don't reject the null hypothesis that the variances are equal. So that means stick with the top line. Don't go to the bottom line. Okay? If that had come out to be 0.024, then we would have said, we're going to reject the idea that the variances are equal. We're going to accept the alternative that they're not equal and use the bottom line instead of the top line for our T-score, our degrees of freedom, our significance, et cetera, et cetera. Okay, so now let me go back to that sheet with the formulas that we had. Where'd it go? PDF file, let me see, it's back here somewhere. Oh, here we go. Now, remember that when I did it for equal variances, see, this should be a P in here. See this S1? That should be SP squared. This should be SP squared. We calculate the pooled standard deviation. I'm going to show you another. Let me show you right now. Another way to write this formula. Notepad. Notebook. Another way to write this same formula. Right? T is equal to x bar 1 minus x bar 2 over the square root of the standard deviation squared pooled over, what was it, N1 plus SP squared over N2, right? That's another way to write that formula is going to be x bar 1 minus x bar 2 over, I can factor out inside the square root, I can factor out SP squared, right? I can say SP squared times 1 over N1 plus 1 over N2, right? No reason I can't. If I multiply this out, what do I have? SP over N1, SP squared over N1 plus SP squared over N2. So it's the same thing. Not only can I do that, is I now can pull this out and just separate those into two square roots. So now the square root of SP squared is just SP, right? So another way I could have written this formula, maybe make it a little easier to solve, over this pooled standard deviation times 1 over N1 plus 1 over N2. Okay, that's kind of the formula I was really looking for. Okay, and I'm using the pooled standard deviation because I'm making the assumption that the standard deviations standard deviations for the two populations are equal. Okay, just in case you see the formula this way, just so you know that that's equivalent to this formula. It's really the same formula. Okay, so now let me go back here. And That was pretty simple. And then we said our degrees of freedom is equal to n1 plus n2 minus 2, which is 16 degrees of freedom. And we saw that here on SPSS. Remember the output for SPSS? Let me get the output window open. Remember this output for SPSS? What was the sample size for equal variances assumed? 16. Well, look at the degrees of freedom for equal variances not assumed. Pretty funky number, right? 14.428. Well, where did that come from? Okay, well, let's go back to the formulas here. There you go, exactly. Okay, so now, where the hell did it go? Come on, let's see. I have so much stuff opened.